The atmospheric pressure is the pressure exerted by the air in the Earth's atmosphere. It can be measured in kilopascals. The average atmospheric pressure varies with altitude. The higher up you go, the lower the pressure is. Some students are investigating this variation in pressure using some data that they found on the internet. They have information about the average pressure at various altitudes. 6 of the entries in the data set are as shown in the table below. By looking at the pattern, the students are trying to find a suitable model to match the data. Hannah suggests that this is approximately a geometric sequence. She says she can match the data fairly well by taking the first term as 101.3 and the common ratio as 0.883. Complete the table below to show the values given by Hannah's model correct to one decimal place. So, Hannah says that these values follow a geometric sequence where the common ratio is 0.883. The first value is 101.3. That's atmospheric pressure at sea level, where the altitude is 0. Now, to get the altitude at 1 kilometer, we multiply this number by 0.883 because these numbers are to follow a geometric sequence with r equal to 0.883. We want this value to one decimal place, so we write down 89.4. To get the altitude at 2 kilometers, we multiply the common ratio 0.883 by 89.4. To one decimal place, this is 78.9. Actually, it is more accurate to only round after we do the multiplication. So the first value was 101.3. We multiply that by the common ratio, which is 0.883. That's the value we got, and then we round it. Now, rather than multiplying 89.4 by 0.883, it's more accurate to stick with this value and multiply it by 0.883. And to one decimal place, we add 1 onto this 9, so we get 79.0. And we continue on, so now we multiply this number by the common ratio, which is 0.883, and we write this down to one decimal place. To one decimal place, this is 0.8. I'm sorry, made a mistake there. We write this number down to one decimal place, we get 69.7. And so on, we continue on to fill up this table. By considering the percentage errors in the above values, insert an appropriate number to complete the statements below. Hannah's model is accurate to within so many percent. What we want to do is compare the values in the model to the measured values, which are in this table up here. See how they differ. Look, first of all, consider the errors, that is just the differences in these numbers. Then get those errors as a percentage of the measured values. So let's start with this value here, 89.4. Well, we write down the measured value, which is 89.9, and subtract the value from the model, which is 89.4. That's the error. We divide this by the measured value, so we want to compare the error to the measured value. And we get this fraction as a percentage. We multiply by 100. I will write this number down to one decimal place. I will write down 0.6%. I will put a minus sign here to indicate that the value in the model is less than the measured value. 89.4 is less than 89.9. We do the same for the next value. So we can take the measured value and subtract the value from the model. So the measured value is 79.5. The value in the model is 79. And we divide by the measured value. We're always comparing to the measured value. We multiply this by 100. To one decimal place, this is 0.6%. And again, we can see that the value in the model for the pressure in kilopascals at an altitude of 2 kilometers is less than the measured value for the pressure at 2 kilometers above sea level. So we can write in minus 0.6% here. And so on. We continue. If the measured value is greater than, if the value in the model is greater than the measured value, then I will make the percentage error positive. You can see that for the altitude at 4 kilometers, both the measured value and the value from the model are the same, so the percentage error is 0%. At 5 kilometers, the value from the model is actually greater than the measured value, so we have a positive percentage error. But we can see that all these values lie within a certain range. They actually lie between, say, minus 1% and plus 1%. Or we could say they lie within 0.7%. We could say they all lie between minus 0.7% and plus 0.7%. But usually when we're looking at the accuracy of a model, we will probably round that value to the nearest integer. So rather than saying the values lie between minus 0.7 and plus 0.7, so we would be saying the model is accurate to within 0.7%, we would round that to the nearest integer and say the model is accurate to within 1%, because 0.7 rounded to the nearest integer is 1. So we're just giving a round figure. So all these values here lie between minus 1% and plus 1%. So that's what we mean by the model being accurate to within 1%. Thomas suggests modeling the data with the following exponential function. P equals 101.3 times e to the power of minus 0.1244 h, where P is the pressure in kilopascals and h is the altitude in kilometers. Taking any one value other than 0 for the altitude, verify that the pressure given by Thomas's model and the pressure given by Hannah's model differ by less than 0.01 kilopascals. Okay, we can pick any value for the altitude. So I'm going to take h equal to 2 kilometers. And I'm going to calculate the pressure by using Thomas's model. So the pressure is given by this function, 101.3 times e to the power of minus 0.1244 times h, where h is 2. Calculating this, we get 78.987. I've rounded this to 3 decimal places. Now we want to compare this to Hannah's model. So let's look at the pressure when h is 2 for Hannah's model. Well, from this table here it is 79, but remember this was rounded. To get a more accurate value, we need to actually go back to see how this value was calculated. Well, this is a geometric sequence. So for Hannah's model, to get the altitude, the pressure when h is 2, we take 101.3 and multiply by 0.833 twice. But that's the same thing as multiplying by 0.833 squared. So we have 101.3 times 0.883 squared. I'll write this down to 3 decimal places. The next thing we need to do is look at the difference between Hannah's value and Thomas's value. So we just take this number and subtract this number, and we get 0.005, and we had to show that the difference is less than 0.01, which indeed it is. So I have shown this just for one value of h equals 2, but apparently it's true for all values of h except h equals 0. Well, actually it is true for h equals 0. The difference, although, well, actually I don't know, I haven't done it. But it is supposed to be true for values of h from 1 to 5. Explain how Thomas might have arrived at the value of the constant 0.1244 in his model. Well, he might have assumed that the model has the form of an exponential function. In other words, P as a function of H is P equals 101.3 e to the power of kH, where K is a constant. So K is a constant to be determined. And he determined the constant K by looking at the measured values. So he could have picked any two. Well, he could have picked, say, this pair here, plugged one in for H, and equating this to a pressure of 89.9. He could then solve to find K. So for given values of P and H, K is the unknown. And then he could have checked all the other values to see if they match this model. If this model gives values that are close to the measured values. So he would have had to assume that we have an exponential decay model here, because K turns out to be negative and the values of pressure are decreasing with altitude. So if you were to graph these values, we would see some sort of exponential decay curve. So this is pressure against altitude h. Well, it mightn't decline as steeply as this, but it's some sort of curve that can be modeled by an exponential function. By the way, if this is an exponential function, if we look at the graph of the log of p against the log of h, then we would have a straight line. Actually, more correctly, it's log to the base e of p, which is written ln of p, and log to the base e of h, which is written ln of h. If we were to look at the values and get the log of both rows and plot log L or ln of p against ln of h, and if we were to get a straight line, that would actually tell us that the relationship between p and h is some exponential curve. So it's probably quicker and more convenient to look at the logs of the altitude and pressure values and plot log p against log h and check to see if it's a straight line. That's more easily done, I think, than just graphing p against h and trying to see if this is an exponential curve. Actually, it should be log of p against h, not log of p against log of h. To see why this will be a straight line if the relationship is exponential, let's just take the log of both sides of this function. If we take the log of the left hand side, we get ln of p. Getting the log of the right hand side involves getting the log of a product. So the log of a product is the sum of the logs. So it's ln of 101.3 plus ln of e to the power of kh. So this is just log of a times b equals log a plus log b. Now ln of 101.3 is just a constant. That's just a number. But look at this term here, ln of e to the kh. We can bring kh in front, so we get kh ln e, which is just kh, because ln of e is 1. So you see we get a linear relationship between the log of p and h. K is just a constant that has to be determined. This here is just a constant. So if the relationship is exponential, the relationship between p and h is exponential, then the graph of the log of p against h will be a straight line. Hanna's model is discrete while Thomas's is continuous. Explain what this means. Well, Hanna's model is based on the idea that the pressure at integer values of the altitudes is a geometric sequence. So it doesn't make sense to consider what the pressure is, say, at 1.5 kilometers at altitudes that are not integers, say at 1.5 kilometers or 3.1 kilometers. The model does not make sense to get pressures at non-integer values of the altitudes. So we can only get the pressures at discrete values of the altitudes, not values in between. So these integer values are discrete. Thomas's model, on the other hand, is continuous because we can use the model that Thomas gives, this function here, to calculate the pressure at any value of h. H doesn't have to be an integer. It doesn't have to be 1, 2, 3, 4, 5. We could plug in a value of h like, say, 1.5 into this model, and we would get a meaningful value for the pressure. Or we could plug in, say, 3.1 for h and get a meaningful value for the pressure. So the values of h here are not discrete. The values of h here are continuous values. So there's no gaps between them, if you like, whereas we have only five altitudes here to consider when we're getting the pressure using Hannah's model. We can have an infinite number of values for h here, anything ranging from 0 to 5 for Thomas's model. So there are no gaps in the values of h, if you like. We just have a continuous set of values ranging from 0 to 5 for this model. State one advantage of a continuous model over a discrete one. Well, one advantage is that we are not restricted to whole number values. We can work with values, any value we like between, say, these whole number values. Use Thomas's model to estimate the atmospheric pressure at the altitude of the top of Mount Everest, which is 8,848 meters above sea level. So we just plug in 8848 for h. Calculating this to one decimal place, we get 33.7 kilopascals. Using Thomas's model, find an estimate for the altitude at which the atmospheric pressure is half of its value at sea level. Sea level is 0 kilometers. The value at sea level is 101.3 kilopascals. So we get a half of 101.3 kilopascals. It's 50.65. So now we need to solve this equation. We want to find h, the altitude at which the pressure is 50.65. So we start by isolating the exponential term. We divide across by 101.3 and we'll get a half, because we know that this number is half of this number. Now, since h is in the power, the next step is to get the log of both sides. So we just stick ln in front of both sides. Ln is log to the base e. So we use one of the rules then, which says that we can bring the power down in front. Or you could think, another way you could think of it is that we have to ask what power must we raise e to in order to get e to the power of minus 0.1244h. Well, the answer is just the power itself, because they're inverse functions of each other. Ln just means log to the base e. So we get minus 0.1244h. Well, we have ln of e here, but log to the base e of e is just 1. So this is ln of 0.5, and then we just divide across. We divide ln of 0.5 by minus 0.1244. Here is ln of 0.5. We divide it by 0.1244. I'll write this down to two decimal places, 5.57. And this is in kilometers. People sometimes experience a sensation in their ears when the pressure changes. This can happen when traveling in a fast lift in a tall building. Experiments indicate that many people feel such a sensation if the pressure changes rapidly by 1 kilopascal or more. Suppose that such a person steps into a lift that is close to sea level. Taking a suitable approximation for the distance between two floors, estimate the number of floors that the person would need to travel in order to feel this sensation. We want the change in the pressure, which we can write delta P, to be 1 kilopascal. So the person steps into a lift that is close to sea level. That means that the pressure is 101.3 kilopascals. That's what it is at an altitude of 0, which is sea level. So we could write delta P, the difference in the pressure, as, say, the PF, which stands for final pressure, minus PI, which stands for initial pressure. So the final pressure, well, the difference in these pressures must be 1. So the initial pressure is 101.3. That's the pressure at sea level. Um, Now the final pressure, well actually I should really put a -1 here because the pressure is decreasing with altitude. So the final pressure would have to be 100.3 if the difference is going to be -1. So we want to take this pressure here, which I call PF, but I'll just call it P for now, 100.3, and we want to find the value of H that corresponds to a pressure of 100.3. This is a pressure that is 1 kilopascal less than the pressure at sea level. The pressure at sea level was 101.3. So 101.3 minus 1 is 100.3. So we want to find the height, the altitude that gives this pressure. So we use our model, which is this here. So we set P equal to 100.3. We've got to solve to find H. So we divide across by 101.3. So we take 100.3, and the first step is to divide across by 101.3. So this is 0.99. I'll write this down to 4 decimal places, 0.9901. Actually, I think I will leave it as a fraction. It's more accurate. I'll write this as 100.3 divided by 101.3. As a matter of fact, we could move the decimal point. Write this as 1003 divided by 1013. Now the next step, of course, is to get ln of both sides. So same method as we did for the previous question. We're trying to find h. If we get ln of the left-hand side, we bring down the power, so we get minus 0.1244h, and we have to get ln of this quantity here. And then we just divide across by minus 0.1244 to get h. So we have 1003 divided by 1013. We get the ln of this, and we divide it by 0.1244, well, minus 0.1244. This gives us the height in kilometers. Remember, h is measured in kilometers, so it's 0.079. I'll round this to 2 decimal places. This is 0.08 kilometers. And we can convert this to meters. There's 1,000 meters in a kilometer, so 1,000 times 0.08 is 80 meters. Now we have to convert this distance to number of floors in a building. So we're talking about a person traveling 80 meters in an elevator. So how many floors will that person move through? So what is the height of one floor? Well, I don't really know, but it's more than 2 meters. Let's say it's 3 meters. So how many floors are in 80 meters? Just divide 80 by 3. And that's approximately 27 floors. The reason I know that a floor must be more than 2 meters is because a tall person is about 2 meters high. So, you know, we would expect the floor to allow a standing room for people. So that's why I wrote down 3 meters for the height of one floor.